Physics, Part 191. Explain why light will not pass through two sheets of Polaroid. We have exam-style questions for this section, and our question number 3 is explain why light will not pass through two sheets of Polaroid when they are arranged in contact with their polarizing directions at right angles. What would happen if a third sheet of Polaroid with its polarizing direction at 45 degrees to the polarizing directions of the other two were placed between them? If you can get hold of the Polaroid filters, it is worth trying this experiment. Starting with thinking about you would determine the polarizing direction of each. Number 4. A vibrating turning fork of frequency 320 Hz is held over the open end of the resonance tube. The other end of the tube is immersed in water. The length of their air column is gradually increased until the resonance first occurs. Taking the speed of sound in air as 340 meters per second, calculate the length of the air column. Neglect any end correction. Question number 5. We can hear sounds round corners. We cannot see round corners. Both sound and light are waves. Explain why sound and light seem to behave differently. Question number 6. The figure shows narrow beam of monochromatic laser light incident normally on a different grating. The central bright spot is formed at 0 degree. A. Write down the relationship between the wavelength lambda of the light and the angle theta for the first diffraction image formed at B. Identify any other symbol used. B. The screen is 1.1 meter from the diffraction grating, and the grating has 300 lines per millimeter. The laser light has wavelength 6.3 into 10 power raised to -7 meter. Find the distance 0b from the central point to the first bright image at B. C. The diffraction grating is now replaced by one which has 600 lines per millimeter. For this second grating, calculate the distance from the central spot to the first bright image. Next we have got chapter number 9, and it has photons, electrons and atoms. In the last chapter we spent a long time in describing properties of waves and in emphasizing experiments which showed that light is a wave motion. We now look at phenomena which during the last 100 years have completely revolutionized physics. A number of experiments around the 1900s showed that light behaves more like a stream of particles than as a wave. Later it was shown experimentally that electrons, which had always been thought of as particles, could also behave as waves. This idea of the wave-particle duality is one of the most important concepts of modern physics. We start by describing the photoelectric effect, the phenomenon that demonstrated light had a particle nature. This is the work which Einstein first explained in 1905, and for which he received 1921 Nobel Prize. We shall then describe the diffraction of electrons. Remember that diffraction is a characteristic of waves, Yet electrons have always been regarded as particles.